Hello everybody, welcome to this video. In this video we're gonna do some examples regarding electric charge and electric current, and hopefully while doing some examples you guys will have a better understanding of how to deal with the charges and the currents and have to do quantitative analyses on them. In doing these problems, please do me and yourself a favor and try and at least think about how to approach the problem to be able to actually find a solution for it, instead of just watching me do it, because in that case it's not going to help you very much. So what I recommend you do, if you have a piece of paper with you, just go through these and at least try and think about the relationships between the given and the wanted quantities, and kind of try to imagine a scenario of what's going on. So let's look at here then. It's saying how much charge, the first example is saying how much charge do 5,000 electrons possess. So how much charge do 5,000 electrons represent, basically? So let's think about it then. If you have 5,000 electrons, let's just put them in some kind of a dish, I guess. Let's just put like 5,000 electrons in there. And we can think, well, one of them, let's zoom that in. One of these guys, one electron, is going to have a charge of, it's going to have some negative Q here, which is, you know that the elementary charge is given by 1 point, let's see here, 602 times 10 to the negative 19 coulombs. And we have to remember that for electrons that's going to be negative, so let's put a negative sign here. That is coulombs per electron. Let's remember that units are our friend. We need units to be able to determine these quantities and help us kind of make sense of all this business. So if it's asking us for how much, if you think about these, then all of these electrons are going to have this amount of charge, and so what we're going to do is multiply this by the number of electrons. And it makes sense too, because if you multiply E, or negative in this case, we can put the negative E and call it negative E. We multiply that out times the number of electrons, so that's 5,000. It's going to give us the total charge, let's say Q total, for this whole kind of dish or space here, Q total. So when we do that, we get negative 1.602 times 10 to the negative 19 coulombs per electron, multiplied by 5,000 electrons. And we can see here that the electrons cancel out, and we end up, and that's a unitless here, and we end up with coulombs. So that makes sense, because charges have units of coulombs. So Q total is going to be, got to put this in our calculator, and what we end up getting is negative 8.01 times 10 to the negative 16 coulombs. Now let's do a quick analysis on this. Let's see. We have an order of magnitude of 10 to the negative 16 here of the total charges, and the order of magnitude of 10 to the negative 19 for a singular electron sitting over here by itself. Let's think though, which one is bigger? I want you to real quick stop the video and think about which quantity here is bigger. Okay, well obviously the one that has 10 to the negative 16 is bigger because it has less decimal places. So it's saying some quantity with, so going back here by 15, so let's see, we have 15 zeros here. Imagine we have 15 zeros, and then we have an 801 coulombs, 15 decimal places. And this other guy has, if you go back here, 1, we're going to have a 1 after 18 zeros now. So 1602 coulombs. We can see that the 5,000 electrons as a whole have a greater amount of charge, which makes sense because there's more of them. So that completely agrees with what you would expect. So now let's go on to the second example. That was a pretty easy example, I would assume. If there's any questions about it, please let me know in the comment section or email me. In the second example, it says calculate the amount of charge represented by 6 million protons. Okay, so let's see. If you have a single proton, it's going to have, the charge is going to be E. And E, we already said, is going to be the magnitude is going to be 1.602 times 10 to the negative 19 coulombs. And let me make sure I use the correct, okay, yes, I did use the correct 10 to the negative 19 over here, so that was correct. Okay, so that's what one proton has. Now if you have 6 million protons, what's that going to be? So that's this amount of coulombs per one proton. So what we're going to do then is have to multiply this again, and we can see that the units work out. If you multiply this by the number of protons, our units are going to be in coulombs, which is the total charge, is what we're asked for. So 6 million is just 6e to the 6, or 6 times 10 to the 6 protons. We're going to multiply that. I'll just write it like this, like as you would in the calculator. That many protons times E is going to give us 1.602 times 10 to the negative 19 coulombs of charge per a single proton. So these guys are going to cancel out now. If you put this into your calculator, you will get, let me put this in here, what I end up getting is 9.612 times 10 to the negative 13. Units cancel out here, you get coulombs. That is a total charge 6 million protons would have. Does that make sense though? Let's see. This number, as we saw from before, has a higher order of magnitude than a single proton. It's about 6 orders of magnitude bigger, which makes sense because we have 6 million protons. So that, in that sense, it makes sense. Okay, so now let's go to the next example. It says you have a total charge entering a terminal is given by this equation, this time-dependent equation. You need to calculate the current at t is equal to 0.5 seconds. Okay, let's think. We have some device that has some terminals, and it's just telling us that this device, some black box here, there's some charge going into it, and the amount of it is given by this equation over here, and the units are in millicoulombs. Let's remember that, millicoulombs. We need to find the current at a certain time. Let's think, what do we need to relate to what here? Try to pause the video and try to kind of think about how to solve this problem. Okay, well, thinking about current and charge, we have to remember that current and charge are related in the following way. Current is the instantaneous rate of change of charge. So if you want to find the current, then all we have to do is find kind of like the velocity of the charges. Basically kind of like a river. The river is made up of H2O molecules, water molecules, and if you want to find the current of it, you got to look at the velocity of the charges accumulated together, and that's going to give you the current, or the velocity of the entire fluid in a river. And it's kind of the similar thing over here, similar idea, which is a flow of multiple charges together, and many charges is going to be an electric current. So what we're going to do is take the rate of change of this quantity here, the charge, and what we're going to end up with is the current. So d over dt is going to be a simple derivative here, 5t sine of 4 pi t, and that is in millicoulombs. Let's remember that again. When we take the derivative, it's going to be a product rule because we have some function of t multiplied by another function of t. So when we take the derivative, we get, let's take the derivative of this one first. So we get 5 sine of, leave the second one unchanged, 5t, that is millicoulombs. Now let's see here, we'll have to do the unit analysis at the end, and after that we're going to add to that the multiple of the derivative of this guy times this guy, which is, leave this unchanged now, 5t multiplied by the derivative of sine is cosine of 4 pi t. Now chain rule though. Remember chain rule, we got to take the derivative of the inside of here, which is going to be 4 pi. So the final answer is going to look like the following. So 5 sine of 4 pi t plus 4 pi times 5 is 20 pi t. It's a bad pi there. So we have here 20 pi t times the cosine of 4 pi t. Now we got to evaluate this quantity, which is the current, remember, at t is equal to 0.5 seconds. 0.5 seconds. And once we do that though, we get, let's see. So let's see here. If we do 5 times sine of 4 pi t, well t is 0.5 or 1/2. 1/2 times 4 is going to be 2 pi. So let's see. 5 times sine of 2 pi. And what is the rest? It's going to be plus. Well, t here is 1/2, so 1/2 times 20 is going to be 10. So you get 10 pi times the cosine of, let's see here, you have 4 and times 1/2, because t is equal to 0.5, you get 2 pi again. And let's think here then. Sine of 2 pi, that is going to be the y component at the unit circle. It's going to be the y component at 2 pi, which is going to be, you can see that at 2 pi, the y component is 0, so that's going to be 0. And let's remember the units are in milliamps now. Milliamps. And over here now, it's going to be, well, cosine of 2 pi, it's going to be the x component at 2 pi, which is here 1. So we're going to have 10 pi milliamps, or if you put that into a calculator to get a decimal format, we're going to get 31.416. I rounded that up, but then if you round up more, because let's see how many significant figures we had. We only had 2, so we'll just go on and round that off to, let's see, 31 milliamps. That's going to be the current at that time. Alright, so let's go to the next example then. That's the wrong place here. I'm going to scroll all the way up. Okay, example 4. This example says determine the total charge entering a terminal between times 1 second and time t is equal to 2 seconds if the current passing through is given by this equation here. Again, I want you to pause the video and think about how to solve this problem, how to approach the problem even. Okay, so let's think again. We have some terminal of a device, and you need to find a total charge, Q total, between the times 1 and 2 seconds. If the current going through here is given by this equation over here. Again, let's think about the relationship between the current and the charge. The current is basically like the flow of the river. It's the speed of all the particles together at a given surface area. So if you have this and we want to find the total charge, well, we have to integrate with respect to time from some initial state. So I naught to I final, and integrate this guy from let's see, Q, let's call it Q naught and Q final. When we integrate I though, what do we get here then? We get, let's bring this over here. This whole thing is going to give us the Q total. So let me write it here. Q total is equal to the integral of, at t is equal to 1 to t is equal to 2 seconds, of the current equation, which is 3t squared minus t amps. Those are the units. dt. And let's see what we get here. And remember though, the integral of dq dt is going to be, if you distribute that t over here, it's going to be, let me rewrite that step if that was confusing to anyone. I'm just going to multiply this dt out on both sides to get rid of it here. It's called separation of variables in differential equations. I'll get some initial current state and some final state that is equal to the initial state of the charge. Those are the bounds of the integral. Once we integrate this guy, we get just Q, for example, and the current is going to be that equation that's given to us. So now, once we integrate that, we get that Q total is equal to 3t cubed over 3, just rules of integration, minus t squared over 2, integrated from t equals 1 seconds to t is equal to 2 seconds. Okay, so let's see now, this guy's going to cancel out, so you get Q total is equal to 2 seconds cubed minus 2 seconds squared over 2. Subtract 1 from all of that, so you get 1 seconds cubed, which is just going to be 1 second, minus, and that's just for the units, seconds being cubed, minus 1 second all squared over 2. We put this into a calculator just to get the answer real quick, and we get 2 cubed minus 2 squared over 2 minus 1 half. What do we end up getting here? Let's see. What I have now is that the Q total, the total charge, is 5.5 coulombs. That is the total charge we have, because we were given that, as you can see, let's see if it makes sense. You have some function, which is the current, which is 3t given by 3t squared minus t, and we can see that 3t squared is dominating this function, dominating the term, meaning this is growing faster than this guy is. So it's going to be some exponential going that way, and we can see that if we take the area under the curve from 1 to 2 seconds, we got to remember what the integral is. It's just the area under the curve. We're going to get the total amount of charge that entered the terminal. So that is that example. Let's go now to another example, which is saying, see, let me clear these guys out from the previous examples. This problem is saying, let's see here. Saying that we have a current flowing through an element, and that current is given by this piecewise function. And I'm going to real quick sketch it so we have an idea of what's going on. We have time here, and we have current here as a function of time. And they're telling us that from 0 to 1, we have, that's 0, that is 1. We have 4 amps, so a constant 4 amps going in. And not including 1. So it's not continuous, it's piecewise, the piecewise function. After that, it's going to be going to 4t squared, which, let's think, if we have 4t squared down here, it's going to be a t squared, but much steeper, so it's going to be going up like this, I would assume. Let's see now. So it's basically given by this constant function and then this 4t squared function here. Now we're trying to calculate the charge entering the element from t is equal to 0 to t is equal to 2. So 0 to 2, we want to find the total charge, which is the area under the curve of this graph. So let's see, current, or I'm sorry, let's see, we want to find charge. So we realize that, as we looked at it before, dq dt is equal to I, multiply dt out both sides, you cancel that. then you get dq is equal to I times dt. Then you integrate that from some initial state to some final state. So what we're going to end up getting is q is equal to the current function, so that's going to be the integral from 0 to 1 of this function, which is 4 amps, dt, plus the integral from 1 to 2 of the other function, 4t squared amps. Let me just take this amps out of here for simplicity's sake. It's going to be a 4. So now I just integrate the piecewise continuous piecewise function to find a total charge, and I'll get 4t integrated from 0 to 1 seconds plus 4t cubed over 3 integrated from 1 to 2. Now we're going to evaluate that, and what we get is 4 times 1 second minus 0, so that's nothing there, plus 4 times 2 seconds cubed over 3 minus 4 times 1 seconds cubed over 3. So real quick, we'll put that into our calculator, and what we're going to end up getting is 4 plus 4 times 2 cubed over 3 minus 4 times 1 over 3. What I end up getting is that the total charge is approximately 13.3 repeating coulombs. And we can see that it's going to be the same, going to be a rectangle here, estimating the number of charges going into the terminal, but then here we can see that it's going to increase and increase because the current is increasing. I hope this video was helpful with dealing with electric and electric currents and electric charges. In the next video we'll talk about voltages. If you have any questions, please don't hesitate to ask me through comments or email. Thank you very much.